Hello everyone, this is Sir Aris. Now let us talk about functions of a complex variable. So to start, let us define the derivative of a function f of a complex number z, defined similar to that of a function of a real variable by the equation f prime of z equals derivative of f with respect to z equals the limit of delta f over delta z as delta z approaches 0, where delta f equals f of z plus delta z minus fz, and delta z is delta x plus I delta y. Function fz is said to be um, analytic, or in other terms, regular, holomorphic, or monogenic in a region of the complex plane if it has unique derivative at every point in the region. So the statement fz is analytic at a point z equals a means that fz has a derivative at every point inside some small circle about z equals a. As an illustration, we consider a function fx of a real variable x, so as shown in the figure that I will be plotting. So if you consider this plot of a function uh, fx, and in terms of x, so suppose the function looks like this. You have a straight line sloped in this sloped upward, but at some point it sharply changes. Its slope changes discontinuously at a point. Let's call this x sub 0. So here delta f over delta x, which is the slope, is different at x naught if we go from left or from right. So from left, so towards, if you go on at x sub 0, the slope here is upward, it's positive, and then uh, just when it reaches this point, it changes to, so after or to the right of this point, it becomes negative, it slopes downward. So at x sub 0, it has two values of derivative, which means that if, in this case, for generally, um, for a function of a complex number, it is not analytic. So it doesn't have a unique derivative, so it is not analytic. For a function fz, when we say that fz has a derivative of z equals z sub 0, we mean that f prime has the same value no matter how we approach z sub 0. So in the complex plane, x, y, suppose this is our point z sub 0. And like here in this case, we only have one way to approach x sub 0 depending on the function. But on the complex plane, there are several ways. For example, we can approach z sub 0 horizontally, so that's one way. Or we start from some point here, curve downward, approaching z sub 0. Or we can also spiral and then reach z sub 0. So what I've shown here are three different ways to approach z sub 0. And for fc to be analytic, it doesn't matter how we approach z sub 0, fz uh, should have a derivative that is unique. So as a simple example, let's find the derivative of z squared. And we need to show that it is 2z, just like when we do a norm on derivative on real variables. So by definition, you have d by d z of f of z that's equal to the limit of f of z plus delta z minus f z divided by delta z as delta z approaches 0. So here, if you have this function, so d by dz of z squared, limit as delta z approaches 0 of function of z, but we change the argument z by z plus delta z. So a z here becomes z plus delta z. You have z plus delta z squared minus the original function z squared divided by um, delta z. We can also write this as, so the limit as delta z approaches 0 of z squared plus 2z delta z plus delta z squared minus z squared divided by delta z. So this z squared here and z squared cancels. So you're left with delta z. So this delta z and this one of the delta z's here cancels with this in the denominator. So you have limit as delta z approaches 0 of 2z plus delta z. You set this delta z to 0. That would be, so our d by dz of z squared equals 2z. Another example, find um, the derivative of absolute value of z squared. If z is a real number, it could have been easier. It's just, so let's say x, absolute value of x squared is just equal to x squared, so derivative is just 2x. However, here, if we use our definition, you have d by dz of z squared. So by definition, we take the limit as z approaches 0 of z plus delta z absolute value squared minus z squared absolute value delta z. Now we're using absolute values here, so the numerator um, z plus delta z squared minus z squared is always real. However, delta z is still a complex number, and remember that delta z is delta x plus I delta y. Now again, there are different ways to approach delta z. So if you have the complex plane x y, arbitrarily suppose this is our value for delta z, we can approach delta z horizontally. Say if you approach delta z along horizontally, delta y equals 0. So in this case, if delta y is 0, delta z is equal to delta x. If you approach along the vertical line, so along this line, we have delta x. Uh, there's no change in delta x, so delta x is fixed. Um, in this case, we have delta z equals I delta y. We already see here that for two horizontal and vertical approaches, delta z is either a pure real number or a pure imaginary number. If we approach in other directions, let's say something like this direction, we get uh, delta z some complex number. So it follows that the limit as delta f over delta z for delta z approaches 0 has different values depending on the direction of approach. Hence, the absolute value of z squared is not analytic. Now let's consider this theorem. If you have fx equals u plus iv xy analytic in a region, then in that region we get this relations. These are called Cauchy-Riemann conditions, and this is what we will try to prove. So first thing, recall that z equals x plus iy. Okay, so taking partial derivatives, you have partial of or partial derivatives of fz, f as a function of z. So partial of f with respect to x, that's equal to, using chain rule. So f is a function of z, z is x plus iy. So you have um, derivative of f with respect to z of partial z with respect to x. Now, partial z with respect to x is, so z is here, x plus iy. So you have df by dz times 1. Okay, and partial derivative of f with respect to y is df by dz partial z with respect to y equals df by dz. So z is right here. Take the partial derivative with respect to y. That would be times I. So using f equal to u plus iv, we take partial derivatives again. Partial derivative of f with respect to x, that's simply partial u with respect to x plus I partial v with respect to x. Take partial derivative of f with respect to y, you get partial of u with respect to y plus I partial v with respect to y. Next step, we combine these two equations. So combining these two sets, so you have partial of, so this and this, so we combine them. You have partial of f with respect to x, the first one df by dz. The second one is right here, partial u with respect to x plus I partial v with respect to x. So the second one, partial f with respect to y. Over here you have I df by dz. So I df by dz equals, we use this, partial u with respect to y plus I partial v with respect to y. So for this second equation, we have, we multiply both sides by minus I, so you have df by dz equals, so this is minus I partial u with respect to y minus I times I, that's plus 1, so plus partial v with respect to y. The goal here is to have two expressions for derivative f with respect to z. But remember that um, fz is given as an analytic function. So df by dz exists and is unique. So that would imply, that would tell us that this df by dz here is just equal to this here, or if you write that as partial u with respect to x plus I partial v with respect to y, no, with respect to x equals negative I partial u with respect to y plus partial v with respect to y. So we just compare these two sides. You have partial u over with respect to x is just equal to this. So partial u with respect to x is equal to partial v with respect to y, and partial v with respect to x equals minus partial u with respect to y. And this is our Cauchy-Riemann conditions. Another theorem which we will not prove: if you know u and v and their partial derivatives with respect to x and y are continuous and satisfy this Cauchy-Riemann conditions, then fz is analytic at all points inside that region where A to base Cauchy-Riemann. An example: find derivative df by dz assuming that we approach z not along a straight line of slope m, and show that df by dz does not depend on m if u and v satisfy the Cauchy-Riemann conditions. This is somehow an illustration of this theorem to convince that this theorem is uh, it works on our on this example. So first, we uh, write down the equation of a straight line of slope m through the point z sub 0, which is equal to x naught plus I y naught, is um, m equals y minus y sub 0 over x minus x sub 0. So along this line, the slope m is equal to dy by dx. So um, what we want to do is we want to find, so we use um, f equals u plus iv and z equals x plus iy. You have df by dz equals du plus I dv, the numerator, okay, and the denominator dx plus I dy. We'll also need uh, so we also write we also let's just write it as we have du, okay, du here. U is a function of x and y. So by chain rule, you have partial u with respect to x of dx plus partial u with respect to y dy. Similarly, dv or v being a function of x and y, dv is partial v with respect to x dx partial u with respect to y dy. So if you write our df by dz, we can write it as, so using this and substituting du, dv, dx, dy by these expressions, you have our du becomes partial u with respect to x dx plus partial u with respect to y dy plus I partial v with respect to x dx plus partial u with this. Oh no, this is not u. This is v. Okay, dv by dy, uh, partial v with respect to y, dy, all divided by dx plus I dy. The next step, we divide the numerator and the denominator by dx. So dx by dx is 1. You have partial u with respect to x times 1 plus partial u with respect to y dy by dx plus I partial v with respect to x. Dx by dx is 1 plus partial v with respect to y dy by dx is dy by dx divided by dx divided by dx is 1 plus I dy by dx. Now let's substitute dy by dx uh, by m. Okay, so you have partial derivative of u with respect to x. Write that properly. Plus partial u with respect to y m plus I partial v with respect to x plus partial v with respect to y m divided by 1 plus I m. So our next step is to find a way to cancel this m, the m's here. What we can do is we can use the Cauchy-Riemann conditions, or here let's call it them equations. Partial u with respect to x equals partial v with respect to y, and partial v with respect to y or x equals minus partial u with respect to y. So strategically, we we don't have to substitute all of them, just a few. So let's say we keep partial u with respect to x, so that we can change this one here with partial u with respect to x. So partial u with respect to x is kept. This, it might be best to keep partial v with respect to x, but replace partial u with respect to y with negative partial v with respect to x. So you have minus partial v with respect to x m plus I partial v with respect to x plus, again this one is this, partial u with respect to x m. And finally, we can simplify, or we can group terms containing the same partial derivatives, partial u, partial x, and this partial u, partial x. So you have partial u with respect to x of this and im, 1 plus im, plus this here, partial v with respect to x. So there's an I here, but there's also a minus m here. So that would be I minus m over 1 plus im. Or this I minus m, if you factor out I, so you have partial u with respect to x1 plus im plus I partial v with respect to x. So we are factoring I, we have here 1, and there should be plus im here. Now if we can cancel out all this 1 plus im, so you have df by dx equals partial u with respect to x plus I partial v with respect to x. And what we can observe is that this expression is independent of m. Okay, let's have a few definitions. A regular point of fz is a point of which fz is analytic. A singular point or singularity of fz is a point at which fz is not analytic. It's called an isolated singular point. If fz is analytic everywhere else inside some small circle about the singular point. We also have a powerful theorem which we will again not prove. If fz is analytic in a region, then it has derivatives of all orders at points inside the region and can be expanded in Taylor series about any point z not inside that region. The power series converges inside the circle about z naught that extends to the nearest singular point. So let us proceed. There are something called harmonic functions. A function phi which satisfies the Laplace equation in two dimensions we have here is called a harmonic function. So there are many physical problems leading to Laplace equation, so we are interested in finding solutions of it. Um, Now we have this theorem. It would show you how important complex numbers are in finding solutions of the Laplace equation. If f equals u plus iv is analytic in a region, then u and v satisfy Laplace equation in that region. Or any function satisfying the Laplace equation is the real or imaginary part of an analytic function. An example, consider the function x squared minus y squared. Verify that u, the function is u, satisfies the Laplace equation, and find the function v such that u plus iv is an analytic function of c. So first, um, we apply Laplacian on u. So using the Laplacian, we have del squared u or partial squared plus um, partial squared y on u, which is x squared minus y squared. This is equal to, so if we take this partial derivatives um, on x squared, that would be, so if you use this on x squared, it would be 0. So you only have uh, initially 2x, and then take the second derivative, that's 2. For this second part, that's negative 2, which is 0, which means that um, u satisfies the Laplace equation. Remember, Laplace equation is del squared u equals 0. Now we use Cauchy-Riemann equations. Partial v with respect to y equals partial u with respect to x. So our goal is to find v. We already have u, so we need to find v. So partial with respect to x of u, which is x squared minus y squared, that is our given. So taking partial derivative, you have partial u or partial v, this one, partial v respect to y equals 2x. So integrating, you have v, which is a function of still x and y. That's integral of 2x dy, which is 2xy plus g of x. Okay, that is, if we take the partial derivative, we should get back 2x. So gx here is only a function of x. So differentiating, once again, with respect to x, you have partial v with respect to x equals, so take derivative with respect to x, 2y plus g prime of x. And once more, we use Cauchy-Riemann condition or equations. Partial v with respect to x equals minus partial u with respect to y. So partial u with respect to uh, oh, by the way, let's write this one here first. Partial v with respect to x is this here. That's 2y plus g prime of x. Now let's solve for uh, partial derivative of u with respect to y. So this is x squared minus y squared. Partial with respect to y of this is 0. With respect to this, that's negative 2y. So this is negative or positive 2y. Now this 2y here and 2y here should cancel out, which means that g prime of x equals 0. Take the integral. Gx is simply some constant. So we finally have an expression for v. Gx here is a constant. So if we write f of z, which is u plus iv. U is x squared minus y squared. V is 2xy plus gx, which is a constant. So 2xy plus some constant. So Vz equals x squared minus y squared plus I 2xy plus some constant. Or we can also write z squared here, this whole thing, um, plus constant.